Derivative and the tangent line problem, basically the problem of coming up with the equation of a line that's tangent to a graph at a particular point. We'll begin by defining what we mean by the secant line to a graph. There's going to be one particular point that we're interested in that has an x-coordinate of c for a given function, and then we're going to consider values of the function that are close to c. So definitely got to go with the picture that accompanies this. Now the value of delta x is going to be approaching c either through positive values or for negative values, but the picture I typically will draw will emphasize positive values, where c plus delta x is thought to be something a little bit to the right of c, but we need to be able to consider it from both directions. So first the picture, and then an indication of what this means. So imagine a function, and I'll kind of a generic graph there of a function just needing to be fairly smooth and passing the vertical line test. Point on the graph, c, f of c. And basically what we want to investigate is how the function is changing as how the function values are changing as x is changing, basically a ratio. If x is changing at a given rate, then the function itself is changing how many times that rate. Are they changing at the same rate, or is it twice as fast, 3 times as fast? We want to know how fast the function is changing in terms of, or with respect to, how fast the x variable is changing, and that amounts to finding the slope of the graph at that particular point. So I'm going to go ahead and attempt to draw a tangent line to the graph at that point. Now we know from geometry, if we have a circle and a point intersecting the graph of the circle in a straight line intersecting the graph of a circle in exactly one point, we call that a line that's tangent to the circle at that point. If we have a straight line that intersects a circle, say, in 2 points, then we call that what? Well, the line itself we call a secant line. So we borrow that terminology from geometry because we're going to have trouble calculating the slope of this straight line, although it seems to be well defined. It's a line that just visually it kind of mimics the steepness of the curve. I wouldn't think about drawing the line like that. It doesn't seem like that's doing the same thing that the curve is doing. But we just have the one point on the line to work with, so it's kind of tough to see how we would calculate the slope of the line. So what we do is we keep that point in mind, and then we move away from that point. Basically, we scoot either to the right or to the left. If we're scooting to the right, the distance we're scooting is delta x, capital Greek letter delta, simply representing the change in x. We're going to increase x a little bit. And that'll take us to another x value, whatever we get, when we take c and add delta x to it. So c plus delta x. Now if we evaluate the function there, then we'll get the y-coordinate of this point. This point is c plus delta x, f of c plus delta x. And if we connect these 2 points on the graph with a straight line, connect those 2 points on the graph with a straight line. Now the slope of that line isn't exactly the same as the slope of the tangent line. It looks like it's a little bit steeper. We give the line a different name. It's the secant line. But we can compare the slope of that secant line to the slope of the tangent line. So we can write an expression for the slope of the secant line. Now recall the slope formula. If we have 2 points on a graph, x sub 1, y sub 1, and x sub 2, y sub 2, the slope is the change in the y coordinates divided by the change in the x coordinates. Rise over run, or difference in the y's over the difference in the x's. If we take these 2 points on this secant line, the point of tangency right there, and call that x sub 1, y sub 1, and call this one x sub 2, y sub 2, and actually use the slope formula to calculate the slope of that line, what we get is, well, let's see, f of c plus delta x minus f of c over c plus delta x minus c. So the vertical change is just the difference in the function values from c to c plus delta x, and the horizontal change is just delta x. The c and the minus c, of course, cancel. That's how much we're going to cross. The change in x is delta x. So we cancel the c's, and we get this expression for the slope of the secant line. Now, the idea here is that it's kind of close to the slope of the tangent line, maybe not exactly, and depending on how this function is behaving, if the function decreases a little bit more, we actually may run into a situation where it could become the slope of the tangent line. But we don't want to go that way. What we want to do is allow delta x to approach 0, basically take this point and drag it down toward, will have the effect of taking this point and dragging it down toward this point. And I don't know if I need another color in there to muddle things, but it's muddled enough as it is. Let's see, if I take this point and drag it down here, suppose we plot this point for a smaller value of delta x, then what we get is a new secant line whose slope is perhaps a little closer to the slope of the tangent line. Well, if we attempt to evaluate the limit of this expression as delta x approaches 0, and we ask ourselves what value, if any, is the slope of the secant line approaching as delta x approaches 0, if that limit exists, then we'll call that the slope of the tangent line. So until we take the limit, pick a delta x, any delta x other than 0, then we have the slope of the secant line, m sub sec, as we have it there. We take the limit as delta x approaches 0, and then we have the slope of the tangent line. So I'll copy and paste the definition here and refer to it just briefly, but basically I've indicated that. The difference, the delta y there that's referred to in that limit is simply this distance. We'll go green there. Delta y and then of course we've got delta x right there. So as delta x approaches 0, that ratio of delta y to delta x should approach the slope of the tangent line. Let's do this for a particular function. Let's take a particular function and a particular number in its domain and see if we can use this definition to write a secant line, find the limit as delta x approaches 0, and actually find the slope of the tangent line to the graph at that particular point. And the slope of the tangent line is also referred to as the slope of the graph. The tangent line is intended to be how the graph is slanting at that particular point in time. If the function is increasing, what we'll see is that it's going to have the tangent line is going to have a positive slope. If the function's decreasing, we'll see the tangent line has a negative slope. All right. So we have f of x equals negative 3x plus 7. Should we make a guess here as to what the slope of this linear function, or the tangent line to the graph this linear function is going to be? Let's use the formula and see what we get. We've got the point 2, 1. So 2, let's go with a different color than green, something that will show up. The 2 is the value of c. 1 is the value of f of c. F of 2, let's just confirm that. F of 2 equals negative 3 times 2 plus 7. That's negative 6 plus 7, and sure enough, that's equal to 1. So at that particular point. So we want to find the limit as delta x approaches 0 of f of, again, c equals 2. So just substitute 2 for c plus delta x minus f of 2 all over delta x. We'll simplify where we can. It's a good idea when doing that calculation for f of 2, whether it's a linear function or quadratic function, to go ahead, if it's a specific numerical value and not some expression with x's in it, if it's a specific numerical value, go ahead and figure out what that is and just substitute it in there. Because if I try to put in the expression minus negative 3 times 2 plus 7, there's a good chance that a sign can be missed or parentheses could be omitted unnecessarily. Just figure out that f of 2 equals 1, and we'll put the 1 in there at the next step. The other one, we actually need an algebraic expression. So delta x is approaching 0, and we need to figure out what f of 2 plus delta x is. So that's going to be whatever we get when we take 2 plus delta x and substitute it for x in the expression negative 3x plus 7. So take 2 plus delta x, substitute it right there. And f of 2, we've gone ahead and confirmed that that's equal to 1. So let's put the 1 there. F of 2 equals 1. We have delta x in the denominator. Keep on simplifying. Basically, we want to keep simplifying the numerator until we can get the factor of delta x out of the denominator. I'm kind of skipping over what may seem to be an obvious fact. When we're evaluating these limits using this definition, the reason that, well, you tell me, why can we not immediately evaluate this limit using direct substitution, substituting 0 for delta x? Because it's undefined, makes the denominator 0, and we hope it makes, if the limit's going to exist, it's also going to make the numerator 0. So we want to be able to express the numerator so that it has a factor of delta x, so that we can divide out the delta x's. So we keep working on it in the hopes that that's going to happen. This equals the limit as delta x approaches 0 of negative 6 minus 3 delta x plus 7 minus 1 all over delta x. The negative 6 and the 7 and the negative 1 all cancel, yes. They add up to 0. So I'm sorry, delta x certainly is still approaching 0. This equals the limit as delta x approaches 0 of negative 3 delta x over delta x. Okay. Finally, we have delta x as a factor of the numerator, delta x as a factor of the denominator, so we can divide numerator and denominator by delta x. Now, all throughout this process, we're thinking of delta x as a single quantity. It's not delta and an x, but it's a single quantity, just as though some textbooks, when they define this, they use the letter h instead of delta x for this. But delta x, we can divide the numerator by delta x and divide the denominator by delta x. When we do that, it's the limit as delta x approaches 0 of -3. And we're there because the limit of a constant is simply that constant. So we get -3 for the slope of the tangent line. Does this surprise anyone that the slope of a tangent line to the graph of a straight line with a slope of -3 ought to be -3? No. No. If we consider what the graph of the function itself looks like, -3x plus 7, so 1, 2, 3, 4, 5, 6, 7, and then the point 2, 1, and evidently somewhere in between the point 1, 4 maybe, something like that. So the graph of this function is a straight line that looks kind of like that. If we pick any point, this point, and look for the slope of the graph at that point, well, the slope of the graph is always -3 because the slope of the graph is a straight, well, the graph itself is a straight line. So finding tangent lines to straight lines is a trivial process, basically. It's always equal to the slope of that line. It only becomes interesting when there's curvature involved, so that at different points along the graph has a different steepness. And so we probably won't do this for many more straight lines. Let's try for this quadratic function. And maybe just a little bit of this at a time. Just the first part. Find the slope of the tangent line to the graph of 3x squared minus 8x at the point 2, -4. Let's first just confirm that f of 2 actually does equal -4. Otherwise, we'll correct the y coordinate. F of 2 equals 3 times 2 squared minus 8 times 2. So that equals whatever 3 times 4 is, minus 16. That's 12 minus 16, which sure enough equals -4. So the point 2, -4 is on the graph, and it's just a matter of finding the slope of the tangent line at that point. So we want to find the limit as delta x approaches 0 of f of, well again, c equals 2. Sometimes it's a different number, but in 2 out of 2 cases, c has equal 2. 2 plus delta x minus f of 2 all over delta x. So the limit as delta x approaches 0 gets more work when it's quadratic. To evaluate f of 2 plus delta x, we need to substitute 2 plus delta x for x in both of the places in this quadratic expression where there's an x. So there's a 3 times an x squared, and there's an 8 times an x. And 2 plus delta x has to be substituted into each of these sets of parentheses. So we put it there. 2 plus delta x there. 2 plus delta x right there. Now we're going to subtract f of 2. And here, rather than, well, like putting something like this in parentheses and putting up there, I think it's far safer just to say, okay, we believe f of 2 is -4. So let's subtract -4. Calculate that separately off in the margin somewhere. Conclude that's -4, and then subtract that. All over delta x.
If we find that that's not -4, do we just plug in whatever value we get?
Yeah, just instructor error, and then whatever the value is. A lot of times it'll just say find the slope of the graph at x equals 2, and it won't specify the y coordinate. And that way, whatever it happens to be, that's what you use for the y coordinate. So we work on the numerator. And we keep working on the numerator until we can factor out a delta x or conclude that delta x is actually not a factor of the numerator. So we got to square the 2 plus delta x using the formula for squaring a binomial. We square the first term, square the 2, we get 4, and then it's twice the product of the two terms. So 2 times the delta x is 2 delta x, and then it's twice that product, so plus 4 delta x plus, and when you express the square of delta x, it's customary to enclose the delta and the x in a set of parentheses. We really don't talk about what might be meant by the change in x squared, but it's not the change in x squared, it's the square of the change in x. That's what's denoted here. So it's customary to enclose that in parentheses. Minus 16 minus 8 times delta x as we distribute the delta x, as we distribute the negative 8 across the parentheses. And then minus a negative 4 is equivalent to plus positive 4, adding positive 4. All over delta x. Got to simplify some more, distribute the 3 across the parentheses, and I think I'll have room if I move it up here. The limit as delta x approaches 0 of 12 plus 12 delta x plus 3 times delta x quantity squared. We can go ahead and combine the negative 16 and the positive 4 to get negative 12, whether we want to put that before or after. I'll go put it in place of where the 16 was. Say minus 12 minus 8 delta x all over delta x. Now, if we combine the 12 and the negative 12, of course, those add to 0, so those cancel. And then we're left combining the delta x terms. So this equals the limit as delta x approaches 0 of ordinarily we put the squared term first. So I'll go ahead and do that. 3 times delta x squared plus 4 delta x all over delta x. So, is delta x a factor of the numerator? It is. It's a factor of each term of the numerator. So we can factor the delta x out of the numerator, writing it limit as delta x approaches 0 of delta x times 3 delta x plus 4 all over delta x. We can then divide out the delta x's. Again, that's the point. We want to be able to divide the delta x out of the denominator so that we can evaluate this by direct substitution. So this equals the limit as delta x approaches 0. Divide out those delta x's, and we have 0 3 delta x plus 4. Finally, the denominator is no longer going to 0. So we can evaluate this by direct substitution. Substitute 0 for delta x, and it's going to be 3 times 0 plus 4, which is 0 plus 4, which is 4. So the slope of the graph at this point, the slope of the tangent line, and it's 4. Oh, an image would be good. Maybe the graphing calculator. See if we come up with a nice graph of y equals 3x squared minus 8x and see what's going on at the point 2, negative 4. I'll try the standard viewing window. The 0.2 -4 is in the standard viewing window, and maybe that'll work for us. Zoom 6. Not bad. 2 -4 is right down there. If we were to draw, I think I can improve on it though. There's wasted space to the left and to the right of where we see the graph is. So I think if we go with an x-min of maybe -2 and an x-max of 4, we'll see the curvature of the graph a little bit better. Let's try this instead. X-min equals -2, x-max equals 4, and try this graph. There we go. So as we look at it and see what's happening at the point, second calc value, x equals 2, there's the point, and if we look at the slope of the graph, now at this point, what I've done, I've modified it in such a way that the scale on the x-axis is considerably different from the scale on the y-axis. Nonetheless, if I think about what's going to happen as I go 1 unit to the right, then I think it's reasonable to think that I go about 4 units up right there. Be nice if we could get the calculator to display the slope, the graph of the tangent line. If we know a point on the line, 2 -4, and we know the slope of this line, can we write an equation for this line? Problem didn't ask us to do that. It's like extra work at this point. But I think that it would be good as far as the visual is concerned. If I can find some room on here for the equation of the tangent line, y'all know from somewhere y minus y sub 1 equals m times x minus x sub 1, point slope form. Well, we've got a point, we've got a slope. So y minus -4 equals the slope 4 times x minus 2. If we solve this for y, put in slope-intercept form, then we can just type in the right-hand side and the calculator should graph this for us. So y plus 4 equals 4x minus 8, so y equals 4x minus 12. If we have the calculator graph this line, it should kind of look like it's behaving as the graph is behaving and going right up alongside it, the tangent line. So here goes. Y equals 4x minus 12. That look okay at the point 2, 4? 2 -4? That seems all right. Occasionally that will be what we need. We'll need to find the equation of the tangent line. In this case, it was just extra. Okay, so in 2 out of 2 examples, we've had a specific function and a specific point. Usually we'll have a specific function in mind, but we may not have a specific point. Suppose there was a follow-up question, the slope of the tangent line when x equals 2. What I meant was, what's the slope of the tangent line when x equals 3? Well, to answer that question, I think we pretty much have to do the whole problem again. Just change the 2 to the 3 up here, but that's a 3, and then that's a 3, and then that's a 9, and we're basically find ourselves doing the whole thing again. So what would be good if we could take and let that number in the domain, the 2 or the 3 or whatever, be arbitrary. Just call it C and express the slope of the tangent line in terms of this arbitrary value, so that if somebody comes later and says, well, what's the slope of the tangent line when x equals 3? Then all we have to do is substitute 3 for C or whatever we let that be. So that is the point of the B part here. Find the slope of the tangent line to the graph at this arbitrary point, C, f of C. We know the y coordinate would be f of C if the x coordinate is C. So it's the same amount of work, maybe a little bit more, because there's some numbers that we had before that kind of all got together and canceled, and here we'll have some values that, well, we hope everything except the delta x or the factor of delta x in the numerator will cancel. This is the limit as delta x approaches 0 of f of no specific value for C, so we'll just say C plus delta x minus f of C all over delta x. We have the specific function, 3x squared minus 8x. So we can evaluate this function at c plus delta x. We take 3, and we substitute in c plus delta x, and we square it. Minus 8 times the c plus delta x. And here I don't have the option. Well, I guess I could find f of c off in the margin, but really it's just a matter of substituting c for x. So the main thing to remember, we've got to put the two terms there. Make sure they're enclosed in parentheses. So it's going to be 3c squared minus 8c. F of c is what we get when we substitute c for x. All over delta x. We're still moving forward on the hope that when we clear all the parentheses and combine like terms in the numerator, delta x will be a factor of the numerator so that we can factor it out.
And where did the 3c squared minus 8c come from?
Well, it's directly from here.
Okay.
And finding f of c. F of c, like f of 2, substitute 2 for x. It's just the rules for evaluating functions. F of c, we substitute c for x. When we define derivative in the not too distant future, f prime of x, we'll just leave it an x rather than choosing some different letter of the alphabet, because we want the derivative to be a function of x, just like the original function is a function of x. But for now, we're calling it c. So the specific value is just yet to be announced. So the tough algebra, c squared plus, it's going to be the product c times delta x times 2, so 2c delta x plus what we get when we square the delta x minus 8c minus 8 delta x minus 3c squared plus 8c. Distributing that minus across the parentheses. The potential for some cancellation, actually some actual cancellation, the minus 8c and the plus 8c. We can go ahead and cancel those. That's good. Distribute the 3 across the parentheses. At the next step, the limit as delta x approaches 0 of 3c squared plus 6c delta x plus 3 times delta x squared minus 8 delta x minus 3c squared all over delta x. What else cancels? Yes, 3c squared and minus 3c squared will cancel. And that's good news because every remaining factor in the numerator, every remaining term in the numerator has a factor of delta x. So we're going to be able to factor it out. And I think probably now is the time because technically no two of those 3 terms are like terms. So let's go ahead and factor the delta x out of the numerator. This equals the limit as delta x approaches 0 of delta x times 6c plus 3 delta x minus 8 all over delta x. Divide the 6c delta x by delta x, divide 3 delta x quantity squared by delta x, divide 8 delta x by delta x, and we have the expression, the trinomial in the parentheses. Divide out the delta x's. So limit as delta x approaches 0 of 6c plus 3 delta x minus 8 and finally, I suppose it would be clear that the -8 and the 3 delta x are associated with this. It certainly is clear from the context. We know we want to find the limit of that entire expression. I suppose if somebody just walked in and was trying to follow this, maybe they could think the -8 is off to the side. It really doesn't matter, just so long as the delta x is in there. But just the limit of that entire quantity. And the limit of that entire quantity, when we substitute when we substitute 0 for delta x, no more limit, it's going to be 6c plus 3 times 0 minus 8, or 6c minus 8. 3 times 0 is 0, and it makes a contribution of 0 to that expression. So having found this expression, what's the first thing we should immediately do to convince ourselves that there's validity to this expression based on what we've just done? Does it work if c equals 2? Right? We should ask ourselves, does it work if c equals 2? If c equals 2, what is the value of 6c minus 8? It's 4. So sure enough, previous example, if c equals 2, we get 4. But now, it's easier to ask the question, well, what if c equals 3? 6 times 3 is 18. 18 minus 8 is 10. So the slope of the tangent line would be 10 in that case. We can go back to the graph. If at 3, whatever point there is on the graph with an x squared of 3, second calc value, plug in the 3. So the point 3, 3, evidently the slope is 10. Now again, don't try to get that with a visual because of the tiny distance comparatively between tick marks on the y-axis. But if we were to find the slope of the tangent, the equation of the tangent line, let's see, just considering this, y minus 3 equals 10 times x minus 3. Y minus 3 equals 10x minus 30. Y equals 10x minus 27, I want to say. Is it 33? Oh. So it would be 10x minus 27. So graph, okay, so we have the slope of the equation of the tangent line to the graph at the point 3, 3. Didn't ask us for that. That was a little something extra there. But the expression 6c minus 8 looks like it's working for us. It looks like pick a c, any c in the domain of this function, substitute that number for c, and it will give us the slope of the graph. And of course we did the c part. Time for the definition of derivative. So we came up with an expression with a c in it. The 6c minus 8 was, in effect, a way of expressing the slope of the graph of the function in terms of c, a number from the domain. What we'd like is a function that gives us the slope of the graph in terms of x. And basically, if I just pick up the c and replace it with x, I can write this. If f of x equals 3x squared minus 8x, that was it, wasn't it? Yes. 3x squared minus 8x, we've effectively found that f prime, definition of f prime in a moment, f prime equals 6x minus 8. The 6c minus 8 that we had told us the slope of the graph. So what it is a function that will tell us the slope of the graph at any number in its domain. So let's look and see how it's defined. The function f prime. F prime is the notation we'll use for the derivative of a function. defined by this formula. The limit which we've been evaluating in the previous examples, it's the limit of the expression that we have for the slope of the secant line, and if the limit exists, it is the slope of the tangent line. It's called the derivative of f at x. I guess I should say it differs only in that we've been using a specific value c, but we want to write this as a function of x, so we replace the c with the letter x. The domain of f prime consists of all x for which the limit exists. Now, if this limit fails to exist for a particular number in the domain of the original function, then we say that function is not differentiable at that particular point. The derivative does not exist at that particular number in its domain, or possibly at a boundary point for its domain. But if it does exist, we say that the function is differentiable there if the limit exists, and the process of finding the derivative of the function is called differentiation. And recall when we defined continuity, we defined a function to be continuous at a number in its domain if the limit of f of x as x approaches c actually equals, it exists, and equals f of c. And then we extended that immediately to say, okay, suppose we have a function defined on an open interval. If it's continuous at every number in that open interval, we say it's continuous on that open interval. Well, a similar idea for differentiability. If this limit exists for a particular number, then it's differentiable there. If it exists for every number in an open interval, a, b, then it's differentiable on that open interval. Now, it gets a little bit tricky if we want to include an endpoint of a half open interval or of a closed interval, and say what it means for a function to be differentiable from the left or differentiable from the right. But for now, differentiable on an open interval if it's differentiable at every number in the interval. The process of finding the derivative using the definition can become quite tedious, and as you can see from the I would call it a mess. Some would look at this and find it quite beautiful. The algebra there, I can't say that I would necessarily fall into that category, but
Are we going to have to do that with tests?
there will be at least one, possibly more than one, where I would want you to use the definition of derivative to find the limit definition here to find the derivative with the x plus delta x and evaluating this limit as delta x approaches 0. But I don't think I'd like you to do it for a third degree polynomial. We've effectively just done it for a second degree polynomial, and it gets progressively worse. We have to apply the binomial theorem if it gets too ugly. But there are a couple of key ones, one involving a square root radical, where I'd like you to employ a technique for finding that derivative, and also one involving a fraction, where it's a rational function with a variable in the denominator. I'd like you to be able to do that one. But this particular one, I'm just kind of showcasing it. There it is for your viewing pleasure. The ones I actually do want to do are examples 4 and 5. I'm going to go ahead and see if I can do example 4 before the break. Here goes. We have the function f of x equals 1 over the square root of x. I want to try to find f prime of x, a function which will give us the slope of the tangent line to this graph at any point where it is differentiable. It needs to be a point in its domain, and I believe it will turn out that there's actually a number in its domain where it turns out not to be differentiable. So let's see. F prime of x equals, just write down the definition, the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. If we're focusing on a particular value of x, this is the slope of the secant line extending from x to x plus delta x. So this equals the limit as delta x approaches 0 of, well, here goes, 1 over the square root of x plus delta x minus 1 over the square root of x all over delta x. Now immediately we have a complex fraction. We have fractions in the numerator, no fractions in the denominator, but that's enough to make it a complex fraction. I would like to write this rather than the difference of these fractions over delta x. We know that dividing by delta x is equivalent to multiplying by what? So if we multiply by 1 over delta x, that's going to be equivalent to dividing by delta x. So before I do anything with those radicals, I'm going to rewrite it like that. It's going to be 1 over delta x times 1 over the square root of x plus delta x minus 1 over the square root of x. Now, there are other ways I might have tried to deal with that complex fraction, but I think this will work as well as anything. Difference of the fractions. I'm thinking get a common denominator. It won't immediately help us, but it will give us a difference of two radicals in the numerator. And then we've dealt with limits in the past where we have a difference of two radicals, multiplying numerator and denominator by the conjugate, somehow get the expressions out from underneath the radicals where we can combine them, and they can help us divide out common factors. I think it will help if we do this. So it's not immediately going to help, but it's going to lead to something that will help. So let's subtract the fractions. The limit as delta x approaches 0 of 1 over delta x times, okay, our common denominator is the product of the denominators, since they ostensibly do not have any factors in common. So just multiply the denominators together. We ask ourselves, this denominator, square root of x plus delta x, can be multiplied by what to equal the LCD? And then we answer ourselves, the square root of x. And the square root of x times 1 is the square root of x. So the square root of x can be multiplied by what to equal the LCD? Yeah, the other one there. So when we multiply that by -1, we get minus the square root of x plus delta x. So we still have delta x in the denominator, and at the moment there still doesn't seem to be a great deal of hope of getting a factor of delta x in the numerator, but there is. There is. If I could copy and paste, well, I can copy and paste it, but I don't know if I feel like it, so I'm just going to copy it like this. What I want to do is multiply the numerator and denominator by the conjugate of that radical expression in the numerator, square root of x plus square root of x plus delta x over square root of x plus square root of x plus delta x, and hope something good comes of it. 1 over delta x times square root of x minus square root of x plus delta x over square root of x plus delta x square root of x, and then the conjugate, square root of x plus square root of x plus delta x over the square root of x plus the square root of x plus delta x. Good things will happen in the numerator. They better. This doesn't look like it's nearly as elegant as the previous one involving the cubic. When we multiply those radicals in the numerator, we get cancellation to take place. The square root of x times the square root of x is going to give us x, and then minus, careful with the parentheses, when we multiply the negative square root of x plus delta x by the square root of x plus delta x, these two right here, of course the radical sign vanishes, and it's going to be minus that quantity. So the quantity, since we're subtracting it, needs to be enclosed in parentheses. In the denominator, we've just got what we've got. Nothing really changes except we have a product. Big set of parentheses around the square root of x plus the square root of x plus delta x. Is there hope now of obtaining a factor of delta x in the numerator? I feel like I need to copy a great deal just to make that happen. So much has to be copied just to distribute a negative sign across parentheses. X minus delta x all over this. Whoops. Just about had that up underneath the radical. And then if we cancel the x and the minus x, we will then have a factor of delta x in the numerator. So I feel like just erasing them. Because you could probably look at this numerator and get negative delta x from that numerator. Can you get there? Yeah, stare it down. You'll get a minus delta x out of that. There we go. The delta x and that delta x, now we end up with a negative 1 in the numerator. When we scratch that delta x out, negative delta x divided by delta x equals negative 1. So negative 1 is a factor of the numerator. So we have now the limit as delta x approaches 0 of negative 1 over the square root of x plus delta x times the square root of x times that quantity, square root of x plus the square root of x plus delta x. Finally, we can evaluate this by direct substitution. Substitute 0 for delta x in each of the places where we see delta x. And delta x is no longer a factor of the denominator, so it's no longer driving the denominator towards 0. So it's negative 1 over the square root of x plus 0 times the square root of x times the square root of x plus the square root of x plus 0. How many more steps? Negative 1 over the square root of x times the square root of x times the quantity square root of x plus the square root of x. Now we multiply the square root of x by the square root of x. I mean, x, in order to be in the domain of this function, is going to need to be greater than 0. Yeah, for sure. Even 0 itself is not allowed because it's got to be in the denominator. So definitely it's got to be greater than 0. So when we multiply the square root of x by the square root of x, we would get x, so no fears of that, times 2 of those. So if we can find a spot for it, put a box for the final answer here, f prime of x equals negative 1, or simply the negative of 1 over 2 times x. I left off the x. Good goodness. 2x times the square root of x. That's the expression for the derivative of this function. And I believe it has the same domain as the function. X has to be positive, and for this one, certainly x also has to be positive. Oh, we're mostly back. This particular little GeoGebra worksheet, hastily thrown together GeoGebra worksheet, we've got the function f of x equals the square root of x, basically. Right here, f of x equals 1 over the square root of x, this graph, and its derivative, the one that we found, evidently f prime of x equals negative 1 over 2x times the square root of x, is that one right there. So if we move the slider, basically the slider will move a point on the graph of the original function. We can look and see what compares to what. I can get my screen back. There we go. Say if I move the slider to a equals 1. There we go. So a equals 1, it evaluates the derivative, and you see the point on the graph of the derivative is the point 1, negative 0.5. Well, the y-coordinate of the derivative is supposed to be telling us the slope of the tangent line to the original graph. So it's supposed to tell us the slope is negative 0.5. And if we look at it, it's a little muddled there. I should probably, don't need to call this point A. Let me turn that off. Object properties don't show the label. There we go. So we've got the point on the graph, and it kind of shows the slope there. What I did for the slope is just I've defined the straight line that's going to be the slope of the tangent line, and I just say type in slope, and it gives me the option. The name of the line is B, so I'll tell it the slope of B, and it'll find the slope of that. But it'll display that, and the slope of that tangent line is 0.5. As we go farther to the right, the slope is getting closer to 0 through negative values. As we go to okay, I was at 3. It's really tough to tell, but the y-coordinate on the point of the derivative is negative 0.1, and as you can see, the slope of the tangent line to the graph is negative 1/10 at that point, negative 1/10. So as we go to the right, the graph gets flatter and flatter and flatter, and that's evidenced by the fact that this is approaching 0 through negative values. Now, if I change the function, what was it, 3x squared minus 8x we had a while ago? 3x squared minus 8x, something like that. And is it going to give me the slope of the tangent line? It really ought to, but it might not. We just want one thing, and if it doesn't work, we'll just resume, pick up where we were. But it ought to do that for me. Let's go 1 to 5. I'm not liking this line. What's the value of A here? 6.6. Okay, now I'm liking it better now. Sorry about that. There we go. Okay, consider this. We found that at c equals 3, that's what we called it at the time, c equals 3, the slope of the tangent line was 10. So just to indicate this, here's the tangent line, and notice the equation. We found this, the 6c minus 8 is what we found. So if we look at the straight line, y equals 6x minus 8, that's its graph. 6x minus 8, that's its graph, and the y-coordinate there of the point on that graph is 10. That's telling us the slope of this tangent line, this line, straight line right here, is 10. Now, I guess one thing I should try to bring in here, what happens when the derivative has an x-intercept? It's not going to show it to me. Close to it, though. The point on the derivative where it crosses the x-axis, what can you say about the tangent line to the graph at that point? It's not quite horizontal here, but close. A slope of 0. And that's going to be important to us a little bit later. Points where the graph stops decreasing and starts increasing, or stops increasing and starts decreasing, horizontal tangent lines, but more of that later. Use the definition of derivative to find the derivative of 1 over x squared. Let's do it. Okay, here goes. F prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. I will provide you with that particular limit definition. It's far more important to me that you'd be able to apply it. I mean, it'd be nice if you could memorize it. It's not that difficult to memorize. But if you miss this one, I don't want you to miss it simply because you didn't memorize it correctly. Spent a lot of time trying to find the limit of the wrong expression. So I'll provide that expression for you on the test. This is the limit as delta x approaches 0 of, well, take the x plus delta x and substitute it for x squared in the denominator, and then minus x squared there, and that's all over delta x. Again, pretty quickly I want to deal with a complex fraction. Dividing by delta x can be rewritten as multiplying by 1 over x. So this equals the limit as delta x approaches 0 of 1 over delta x times, I'll copy and paste, 1 over x plus delta x quantity squared minus 1 over x squared. Should kind of feel like what we did last time. At this point, we had the difference of two fractions, and we got a common denominator, and we subtracted the fractions. Going to do that same thing here. So it's going to be the limit as delta x approaches 0 of 1 over delta x times, well, the common denominator is the product of the denominators. I think I'll write it this time x squared times x plus delta x quantity squared. So looking at the denominators, the first denominator can be multiplied by x squared to equal the LCD. So x squared times 1 equals x squared. The second denominator, x squared, can be multiplied by x plus delta x quantity squared to equal the LCD. So that is what we need to subtract, x plus delta x quantity squared. No radicals here, so we can simplify the numerator and cancel some terms and hope that we have a factor of delta x that can be used to divide out the factor of delta x in the denominator. So this equals the limit as delta x approaches 0 of 1 over delta x times x squared minus, and kind of important here that we're subtracting a quantity that we're about to simplify. It's already multiple terms, but it's going to become a trinomial. When it becomes a trinomial and we lose the exponent right here, we still need parentheses around that trinomial expression that results from that. So we square the x and we get x squared. We take twice the product of the two terms and it's plus 2x delta x, and then we square the delta x. Now at this point I think I want to copy most of this, clear the parentheses, and then do a little simplifying, a little bit of erasing, save ourselves a little bit of time and effort. It's going to be x squared minus 2x delta x minus delta x quantity squared over the LCD. I don't know if you're following your notes at 3 o'clock some morning, a few days from now, are you going to know what happened if I just erase the x squared and the minus x squared? Maybe you want to erase them on your paper. Maybe you'll recopy this, and it makes me feel just a little bit irresponsible to do that. So I don't. I did it on the previous problem. Maybe I shouldn't do it in this one. Minus 2x delta x minus delta x quantity squared. I know it's an extra step that has to be written. There we go. You can imagine that I just erased the x and the minus, the x squared and the minus x squared. So they're gone now. Is delta x a factor of every term that's left in the numerator? That's what we need. And it is. So we factor out that delta x, so it's going to be the limit as delta x approaches 0 of 1 over delta x times, let's see, yeah, delta x times negative 2x minus delta x all over x squared times x plus delta x quantity squared. Finally, we can divide out the delta x's. In particular, we can divide out the delta x in the denominator with this delta x in the numerator. As soon as we do that, the denominator is no longer approaching 0. So we can evaluate this limit using direct substitution. So I'm going to write the simplified form, and then we'll use some direct substitution. So the two places where we see delta x, we'll substitute 0. So this equals negative 2x minus 0 over x squared times x plus 0 quantity squared. And this is going to be negative 2x over x squared times x squared. Now, a step we might skip is the step where we write negative 2x over x to the 4th. Or should I write negative 2x over x to the 4th? I should write that, huh? Negative 2x over x to the 4th. But then we immediately realize we can reduce that one more time to what?
Negative 2 over x to the 3rd.
There we go. Negative 2 over x to the 3rd. Negative 2 over x to the 3rd. And that's going to give us the derivative there. So the technique there is something that I want you to be able to demonstrate on the test. I would say on the test, either something a lot like example 4 or something a lot like example 5. Maybe there's room for more than one of those on the test, but I kind of doubt it. Find the derivative with respect to x of this function. Well, this function, it wouldn't be bad to look at the graph of this function, because there's something going on with this function at x equals 3. If we look at this graph, and consider what's happening to the left of 3, or at 3 itself, it's defined by the expression 2x minus 1. So a couple of key points, and we can draw a piece of a straight line. 2 times, right at 3 itself, 2 times 3 is 6, 6 minus 1 is 5. So 1, 2, 3, 4, 5. Goes through the point 3, 5. And the y-intercept is negative 1. So this is a piece of a straight line. And what is the slope of the piece of the straight line? It's 2, right? Now, on the other side of the 3, if we evaluate the function at 4, for example, 4 minus 4 is 0, because we have to use this expression to evaluate it when x equals 4. So 4 minus 4 is 0. 4 minus 5 is negative 1. 4 minus 6 is negative 2. If you write it negative x plus 4, maybe it's easy to see that has a slope of negative 1. Now, I've left off what's happening between 3 and 4. The function is defined between 3 and 4, and it's going to continue up this way. And if we evaluated the limit of f of x as x approaches 3 from the right, that would be the limit of 4 minus x as x approaches 3 from the right, because that's how the function is defined when x is greater than 3. 3 values a little bit more than 3, so that's 4 minus 3, which is 1. So the point 3, 1, I can't really call it a hole in the graph, but it's a boundary point for the graph, and so the graph goes up to it but does not include it. Would you guess that this function is going to be differentiable at 3? It's not continuous at 3, and what we'll learn, if I can talk fast enough, is that a function has to be continuous in order to be differentiable. And there are actually some good examples of functions that are continuous but still not differentiable. But this one is not going to be differentiable at 3. Let's see what we can say about its derivative. At any point in the interval, let me write this, f prime of x equals blank if x is less than 3. Notice I deliberately left off the or equal to bar. There's an or equal to bar here, but there's not an or equal to bar there. Deliberately left it off because we can easily define a function, easily indicate the derivative of a function in an open interval, but it's tricky what happens at the endpoints. So this function is differentiable on the open interval from -infinity to 3 because it is equal to this really nice linear function on the interval from -infinity to +3. So the slope of the tangent line, notice I'm not going to do the delta x thing here, but the slope of the graph all the way to the left there is 2. Pick an x, any x less than 3, the slope is 2. On the other hand, if I pick any x greater than 3, what's the slope going to be? -1. So that catches all real numbers in the domain of this function except the number 3. Got to figure out what's happening at 3. Now that takes as much work as all the rest combined. Figure out what's going on at 3. So I'm going to take this and put it off in a little corner somewhere. There we go. And let's find the limit as delta x approaches 0 of f of 3 plus delta x minus f of 3 all over delta x. Now it's going to turn out to have issues. We're going to end up having to evaluate both the one-sided limits, delta x approaches 0 from the right and delta x approaches 0 from the left, and then compare them, because the delta x's are not going to divide out in one of these two cases. So, well, let's simplify it a little bit until we get to the point where we realize this. This equals the limit as delta x approaches 0 of f of 3 plus delta x. Well, here we go. Delta x is a small number. Well, if it's approaching 0, it's eventually a small number. But it might be positive, it might be negative. So 3 plus delta x, I've got to answer the question. If I'm going to evaluate this, replace this with one of these, I've got to know, is 3 plus delta x greater than 3, or is it less than 3? It can't be equal 3 because delta x is not allowed to get to 0, just real close. And the answer is this. It depends. If delta x is positive, then 3 plus delta x is greater than 3, so we use this rule. On the other hand, if delta x is negative, then 3 plus delta x is less than 3, so we'd have to use that rule. So we've got to break it apart into two cases. If we're going to simplify this, we have to think, okay, is it approaching from the right or from the left? So let's say it's approaching from the right. No. Let's do the left first. Approaching from the left. It ends up behaving badly as it approaches from the right. So let delta x approach 0 from the left. Now we know that 3 plus delta x is less than 3, so we can use the 2x minus 1. So it's going to be 2 times 3 plus delta x minus 1. And then what is f of 3? It's 5. We put the 5. All over delta x. So we keep going. This equals the limit as delta x approaches 0 from the left of 6 plus 2 delta x minus 1 minus 5 all over delta x. Well, the 6 and the minus 1 and the minus 5 all add up to 0. So cancel them all. A group cancellation there. This equals the limit as delta x approaches 0 from the left of 2 delta x over delta x. And I guess this is not a big surprise. This is the limit as delta x approaches 0 from the left of 2, which is 2. Okay. Well, that part of the limit exists. I guess that's not the final answer, so you shouldn't put a box around it. Hope that wasn't important. What I should do is find the limit as delta x approaches 0 from the right of f of 3 plus delta x minus f of 3 over delta x. Now, delta x is a little bit greater than 0. So 3 plus delta x is a little greater than 3, and if it's greater than 3, we use the bottom rule for evaluating the function. So this is the limit as delta x approaches 0 from the right of 4 minus 3 plus delta x. But f of 3 is still 5. And that turns out to be a problem.
Why is it 5 again?
Well, just because in the original rule that defines the function, the or equal to bar is up there. So still 5. So imagine what a secant line would look like. If we've got a secant line, this is our point, CF of C, 3F of 3. But now, if delta x is positive, we're considering points to the right of that. So points like right there. And we're wondering, what's the slope of that line? And then maybe as delta x gets closer to 0, we look at the slope of this line. And as delta x gets a little closer to 0, we look at the slope of this line. And as delta x gets really close to 0, what's happening to the slope? And yeah, it's going to a point where we're not going to be able to define the slope. See, the slope of this line is maybe what? Oh, negative 7 or 8, then maybe negative 10, maybe negative 20, maybe negative 100. Maybe it's approaching negative infinity. Let's see what goes on here. This is going to be the limit as delta x approaches 0 from the right of 4 minus 3 is 1. 1 minus 5 is negative 4. So negative 4 minus delta x over delta x. Delta x is not a factor of the numerator. It's a term, but I can't factor the delta x out of the numerator. If you want to, I don't know if you'd want to, maybe you would. This is the limit as delta x approaches 0 from the right of negative 4 over delta x minus delta x over delta x. Yeah. So take the delta x over delta x and call that 1 because it's equal to 1 for every value of delta x, since delta x doesn't equal to 0. As delta x goes to 0 through positive values, the denominator is going to, well, small positive value. Negative 4 divided by a small positive value is a great big negative value. So this equals negative infinity. That's what's happening to the slopes of these lines as we go from the right to the left there. They're getting steeper and steeper and steeper, arbitrarily steep. So the slope of the tangent line is approaching negative infinity. This limit does not exist, and this function is not differentiable at 3. So we leave it. We're looking for the derivative. We leave it like, trying to circle it, having a hard time. We leave it like this. That's the derivative. It's 2 if x is less than 3. It's negative 1 if x is greater than 3. It's undefined otherwise. It's a nice theorem here. Basically, it says that it takes some work to get there, but it says that if a function is going to be differentiable at a particular point, it must be continuous there. And it would have been enough had we known that to say there's a discontinuity at 3, so it cannot be differentiable at 3. So the trouble is, what if something like the absolute value of x, where it actually is continuous? And it turns out that's not enough to ensure that it's differentiable. And I feel like I should probably do this at the beginning of class where I give it more attention. But where there's an abrupt change in slope, there's an abrupt change in slope right at 0, because if we approach from this direction, the slope is positive 1, positive 1, positive 1, positive 1, positive 1, and then it changes dramatically to negative 1, negative 1, negative 1, negative 1, turning instantaneously the 90-degree turn that it has to make. This function turns out not to be differentiable at 0, even though it's continuous at 0, and it takes more time than I have. It feels like it does. Let me do that justice at the beginning of class next time.